Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 2.1.2, which is Flowcharts for Congruence. Pretty basic chapter. We're actually going to be spending a lot of it reviewing for Integrated 1, since you guys have already learned all these theorems here. It does say examine the two triangles at the right. It asks if they're congruent, and if so, which triangle congruence theorem ensures that these triangles are congruent. So before we get into A, why don't we talk about all the different possibilities that make triangular congruence a possibility. So from Integrated 1, hopefully you'll remember that SSS makes it happen. Angle, side, angle makes it true. Side, angle, side makes it true. What else am I missing? Angle, angle, side makes it true. And then of course there's hypotenuse leg, which is a substitute for ASS. It's the only time ASS ever works, but hypotenuse leg, but you have to establish the right triangle aspect of the triangles before you use HL. And even though in letter A they look like right triangles, since we're not given a 90-degree angle here at B and at D, we can't make the assumption that that angle is 90 degrees. So we're left to our own devices on A. It looks like if I was to flip triangle FDE, I could get it to look like this. I'm just going to rotate that triangle so that it's standing this way, putting the D angle in that corner, the F at the top, and the E over here. That puts the 4.5 down here, the 6 on the side, and the 7.5 as the diagonal side here. Now, if we look at it, the corresponding sides are all congruent, right? AB is to FD, BC is to DE, and AC is to FE. So what we can do is we can say, all right, by side, 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 right? So by side, 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 triangle ABC is congruent to triangle. Now notice I have to keep using the same path. I went from A to B to C, which is why I reoriented the right side triangle so I could say it's congruent to triangle FDE. Now, if I wanted to make a flow chart showing that the argument was true, then I would just do that. I mean, this is straight out of Integrated 1 right here, where I could say that side AB is congruent to side FD, and the reason for that would be given. I could say that side BC is congruent to side, looks like DE, and that would be given. And then I could say then that AC, side AC, is congruent to side FE, and again, that's given. And for three given reasons, and again, I'm sure you guys remember from Integrated 1 that they don't always give you everything. In fact, most of the time, they don't give you everything. But when they give you three givens, there's no need to work that hard. It's just triangle AB. Oops, darn it. Yeah, that was meant to be a triangle right there. Whoops. Triangle ABC is congruent to triangle FDE, and that's because of SSS congruency. Now, notice how the flowchart worked. The statement, the fact, went in the middle, went inside the box or the circle, and then the reason went on the outside. So that's just kind of how our flowcharts work. They literally flow into the final argument, and then we make our final argument with the final reason, and we're all set to go. I'll be right back with the next problem. And we're back. Case in point with number 2-13, how I talked about they don't always give you everything. In 2-13, they definitely don't give you everything, but you might be able to see what the missing piece is if you look at this diagram hard enough. It does say make a flow chart showing that the triangles below are congruent, and so why don't we go ahead and do that? So we can go ahead and start off with, I always just start off with the givens. So side PQ is congruent to side, now notice I went from P to Q, okay? I don't want to go congruent to side ST. I want to go using the corresponding path. So from P to Q goes from the 120 to the blank. I'm going to go TS, which is the 120 to the blank. So make sure the corresponding paths always match up. And again, that's given. What else do we know? We know that angle P is congruent to angle T. And again, that's given. Now, the last thing we're going to look at is we're going to look at this angle here in purple here. These angles here, those are vertical angles from the last chapter. And as we know from the last chapter, vertical angles are always congruent. Now, here's the problem, is that angle R, I can't just call him angle R, because which angle R am I talking about? The left angle R, the right angle R, the top angle R, or the bottom angle R? Angle R is a pretty pretty vague terms. So we want to make sure that we structure our answer so that we know what angle we're definitely getting. So here's what I'm going to do. I'm going to call the left angle, I'm going to call him angle PRQ. Now, just like the last example up here where I had to use the corresponding path, I'm going to use the corresponding path again. So let's take a look at the path I took on the left side. If I go from P to R to Q, that's going to be from the 120 to the purple to the blank. So I got to do the same thing on the right side. The 120 to the purple to the blank, that is going to be angle TRS. And that is going to be not given, like I was going to write down. It's actually going to be because of our good old buddy vertical angles. And then from here, we can just conclude it. We can say triangle PRQ is congruent to triangle TRS. And this time, the reason for those would be angle, side. AAS Cong, right? The reason why is because I got an angle and a side. It's not angle, side, angle. For angle, side, angle, the side has to be in between the angles. So we will assuredly run to that. So at some point in the class. Anyway, I will be back with the next question. Feel free to pause if you need to. And we are back with 2-14. It says, suppose you are working on a problem involving two triangles, triangle UVW and triangle XYZ, which I've drawn already, and you know that UVW is congruent to XYZ. What can you conclude about the sides and angles of the two triangles? Write down every congruent statement involving sides or angles that must be true. Okay, so I drew the diagram in this particular way, and the reason why I drew it in this way is because if you look at triangle UVW and triangle XYZ, you want to pay attention to their corresponding pieces. Notice how the U corresponds with the X, the V corresponds with the Y, and the W corresponds with the Z. I drew the triangles so that those pieces would match up. And you always want those corresponding sides to match up with each other. That way when you write the congruency statement, the triangles actually match up the way they are via side, or angle, side, angle, and whatnot. What this problem is trying to get you to see is that when you have two triangles that are proven to be congruent, what happens is you end up with a situation where you have UV, side UV, which is this guy going down, it will be congruent to side XY. And then you'll have side UW being congruent to side XZ. And then you'll have side VW being congruent to side YZ. So let's go and put that in. These guys are congruent, these guys are congruent, and these guys are congruent. But not only that, we can also say then that angle V is congruent to angle Y. Angle U is congruent to angle X. So I'll go ahead and throw a double bubble on that guy. And then angle W is congruent to angle Z. What this problem is trying to teach you is that when two triangles are congruent, it means that their corresponding sides and angles will also be congruent. Let's go and get that in our notes because I like that. So when two triangles are proven congruent, then their corresponding sides and angles are also congruent. Okay, awesome. So why don't we go ahead and move on to the next problem. Feel free to pause if you need to. And the last problem in this unit is saying that Callie started to prove that the given information in the given the information in the diagram at the right, AB is congruent to CD. Copy her flowchart to below on your paper and help her by justifying each statement. Okay, cool. So it says AD and CB are parallel. Okay, we can go ahead and say that that's given, and we know that's given because the arrows on the lines. We know that angle A and angle C are congruent. That's given because, again, that's on the diagram. We can see that angle ADB, which is this guy, angle ADB, is congruent to angle CBD, which is going to be this guy. Now, it's going to take a little bit of doing, But if you look at this diagram here of this diamond, if you turn your head about 90 degrees counterclockwise, so that the tip of your head is facing about 9 or 10 o'clock, what you'll find is that AD and BC are parallels, and DB is the transversal, which cuts through them. That makes angle ADB and angle CDB alternate interior angles of parallel lines. And as we learned in the last section, alternate interior angles of parallel lines are congruent to each other. So alternate interior angles could be a reasonable justification for this statement here. Yeah, that information comes back. Hopefully that doesn't make you uncomfortable, but it's there anyway. We know that BD and DB are congruent, and that's our good old buddy Reflexive. We haven't heard that guy in a long time. Our good old buddy Reflexive making his triumphant return. And these triangles are ultimately congruent via angle side. Now this last thing here, the most common, up until recently, acronym that is used to describe this is known as Cpctc. There's another acronym in this book, and I forget what it is, but I'll probably be able to show it to you in class, but I would take Cpctc. And what it stands for corresponding parts of congruent triangles are congruent. And I understand you can't see that. That's because the text is in white, and here you go. Boom. And so you'll see where each of those pieces come from. It's an acronym for that. So this is the C part, corresponding parts of, well, we'll skip that part, of congruent triangles are, again, we're going to skip that part. It's kind of a minor word, are congruent. So there you go, Cpctc. Corresponding parts of congruent triangles are congruent. So the moral of the story when it comes to this unit is we're not just going to prove triangles congruent anymore. Back in Integrated 1, you could just say triangles are congruent via AAS and you'd be done. Now we're going to start getting into proving the triangle is congruent and then using that as a means to show just a piece of the triangle is congruent to a piece of the other triangle. So hopefully that makes sense. As always, leave questions and comments in the comments area, and I will see you all in the next episode.